Hello, my name is Zong, and today I will be solving for you combustion analysis problem and an equilibrium chemistry problem. So this is the combustion analysis problem with a compound containing carbon, hydrogen, and resulting in a complete combustion, which means no carbon monoxide is produced. So we can see all the carbon turns into carbon dioxide, all the hydrogen ends up as water, and all the nitrogen will go here, turned into ammonia in a later step. Because we're given all the masses of the products, we simply need to determine their moles by dividing by the molar mass and seeing if they fit a ratio that can fit an empirical formula for the unknown compound. Let's start by writing the mass of all the products. So carbon dioxide, 4.3, 0.8 water, and for nitrogen, it's 2.50. But it's not actually nitrogen, it's ammonia. So we'll take that into account when we divide by our molar masses. Molar mass is determined by adding all the elements together from their masses found in the periodic table. So for CO2, we get 18, it's 44.1. Water is 18.3, and ammonia is 17. Units, of course, grams per minute. I don't have that much space to write that. So dividing that all, we have 0.1468 moles of nitrogen, 0.3665 moles of water, but in every water molecule, there's two hydrogens. So let's double that to get moles of hydrogen, 0.730. And as for carbon dioxide, we get 0.2936. So X, Y, and Z in this unknown compound is an integer. And the lowest integer for a chemical form is 1. So we see that our lowest number here is 0.1468. So let's see if the other numbers fit into this multiple. And indeed, you can see that they start to follow a trend. Let's divide them all by 0.1468. We get about 5 here, and we have about 2 here. So this means we've determined X, Y, and Z. We have C2, H5, and 1, or just N as our unknown compound. And of course, this is the empirical formula. For combustion analysis, there's no way to really tell if the compound in question was the empirical formula or any multiple. For example, C4, H10, N2. That would also work. Now, let's assume it was the empirical and try to balance this equation. How many oxygens would we need? So let's just assume we have one of these, an unknown amount of oxygen, resulting in carbon dioxide, water, and nitrogen gas. So all the carbons end up as CO2. So I'm going to put 2 here. All the hydrogens and water. So that's 5 out of 3 here. And half a nitrogen. Now let's do some math to determine the oxygens. We have 4 from carbon dioxide, 2 and 2. And we have 2.5, 5 out of 2 from the waters. So that's 6.5 or 13 out of 2 oxygens. How many O2s? That's half of that. So we have 13 out of 4 O2s. Now that we have this, we can balance the equation properly by multiplying them by the highest denominator, in this case 4. So we'll end up with C2H5N, state of the N here. See if you can guess it. Some for oxygen, 8 carbon dioxides, 10 waters, and 2 nitrogens. Now, if you were quite sharp, you would have realized that this is probably a gas due to the fact that it has a very low molecular weight, and the 1 nitrogen is not enough to keep the intermolecular forces from sticking together during room temperature. So our next problem is in equilibrium. As with all equilibrium problems, the first step, it's a pretty good one, is to produce an ice table for all the products. So there we go. The question says a mixture of moles A, B, and C are placed in a container at a certain temperature. The reaction then reaches equilibrium, and we know the final number of E moles. Determine the equilibrium constant. So in order to do that, we'll have to determine the moles in C. Let's see if we can do that. So initially, we have 4. Oh, that's B. 4.33 moles of B, 5.5 moles of C, and 3.31 moles of A. We end up with 6.16 moles of B, which means we would have had to add a certain amount of B. That number, simply subtract 6.16 by 4.33, and we get 1.83. So this 1.83 moles is the 3B that got added as a result of 1A molecule breaking down, which means that the amount of A broken down is a third of 1.83. So 1.83 divided by 3 gives us how many A molecules were lost, and that's 0.6. Because once again, a breakdown of a single mole will end up as 3B molecules. You can see that 0.61 times 3 is 1.8. And it also breaks down into 2C molecules. So 0.61 times 2, that's 1.22 moles of C. So now that we have our difference in concentration, we can find out the concentrations at equilibrium. Simply add these together, subtract this, we get 2.70, 7.17, and now we can determine our equilibrium constant, Kc, which is our reactants, C, B over our products. Now don't forget our coefficients, because we use 3 for B, so it's cubed, and 2 for C squared. Now simply let's put in our numbers. 7.7 squared, 6.6 for B, and 2.70. And our final result is 4.5 times 10 to the 3 is our final equilibrium constant. Once again, I'd like to thank you, GoGoWiz, for giving the opportunity to allow me to demonstrate my knowledge and my personality.